later. So now we move on to the next talk. The next talk will be from Christian Schlegel. And Christian Schlegel is for more than 20 years. No, Christian Schlegel was for more than 20 years the general manager of ICSAT Automation GmbH, which was acquired by HMS Industrial Networks in 2013. And after the acquisition, he was member of the corporate management team of HMS. In 2019, he left HMS and started a business as independent consultant supporting companies with his knowledge in CAN technology, industrial networks, safety, OT security, OPC UA, and Internet of Things. Christian Schlegel is part of the CAN community since 30 years. In 1990, Christian Schlegel already started to develop a first application layer for CAN. When SIA was founded in 1992, he contributed with the knowledge from his work to the SIA CAN application layer to the CAL working group. Later on, he was also involved in the development of the CAN open standard and several related device and application profiles. As business director, he is part of the board of CAN in automation. So Christian will tell us today about the Multi Pdu concept for heterogeneous backbone networks. Christian, the floor is yours.
Yes, thank you, Arthur, for this introduction. Yeah, so we heard a lot about Connexl and the new capabilities Connexl provides. Just Peter explained that we even could put Ethernet frames now, transfer Ethernet frames within a Connexl frame, as we have now a large amount of data per frame that we can transmit. And I would like to present you now an idea or a concept how to use the available bandwidth of Connexl even more efficiently. And more efficiently by using so-called multi-Pdus. First of all, the question is, what is a PDU? Just to have common understanding with each other. A PDU means protocol data unit, and it's a block of data from a dedicated layer transferred over network. So this means if we look at the OSI model, actually each layer communicates with each layer by exchanging data packages, and these data packages, these are the protocol data units, and these protocol data units, so in case layer 7 wants to transmit his protocol data unit, hands over the protocol data unit to the layer 6, and the layer 6 creates from this received protocol data unit an own protocol data unit, and so it travels down the complete hierarchy is transmitted, and then on the receiver side it's more or less depacked. And if we look a bit closer, then we find another term that we also find in the Connexl protocol, because if we have here, for example, the layer 4, and this is the PDU of layer 4, then when the layer 4 hands over the PDU to the layer 3, also by using a service from layer 3, then the received data from layer 4 is the so-called service data unit. And from this service data unit, then the layer 3 creates its own protocol data unit. So these are the two terms that we now see in the presentation, so that we have the common understanding for this. Now, when we look at the CAN protocol, then we do have also a PDU in CAN, although we don't have all these several layers of the OSI model with CAN. CAN, we typically have the physical layer, we have the data link layer, which is split into the MAC part and the LSC part, and then we have the application layer. And very basic in the application layer, we have data, and the PDU already could be a single application data, or if we have a higher layer protocol on CAN, then it also could already be this protocol, which becomes the PDU that is then handed over to the data link layer, and the data link layer transmits this PDU as a CAN message, puts the ID in front of it and transmits the data with the respective protocol. Now, what is a multi-PDU? Just what the name says, a multi-PDU means we put several PDUs in one data package, so more or less several PDUs in one CAN message. And actually, this is nothing new, and this is already used from the beginning, and it's used by various application layer protocols. For example, already the car manufacturers, when they started to work with CAN, they used this kind of multi-PDU mechanism, although it was not called multi-PDU mechanism. So if we have an ECU, then we have different signals on an ECU. And actually what the car manufacturers did, and each car manufacturer had its own proprietary definition of these signals, and also then of the data packages of these signals that were then mapped into the CAN data frame, and also the identifier was specified, so that the identifier already identified which signals are transmitted in the CAN message. Also from the automotive industry, we have AUTOSAR, which Peter also just mentioned in his presentation. In AUTOSAR, it's a more formal definition and a standardized approach, which is then shared among all the car manufacturers, which also makes for ECU manufacturers, makes it easy to develop the software. Actually, we have the signals in the ECU, and now we have so-called iPDU, interaction layer protocol data units, that are specified, and an iPDU also then contains certain data from the data that is the ECU application going to transmit or to receive. And these iPDUs are handed over to the data link layer and are transmitted by the CAN message. But in addition, there is also already a specification of a so-called PDU container for a dynamic mapping of iPDUs into one CAN message. So especially this was introduced for CANFD, as with CANFD we had up to 64 data bytes. Originally the iPDU has 8 data bytes, so in order to use already the bandwidth provided by the CANFD more efficient, these PDU containers have been specified, meaning that the iPDUs could be mapped into the CAN message. And if you since you have more iPDUs in one CAN message, they were not being able to identify it anymore by the identifier. So you need a certain header that identifies the content of the iPDU. Also on the industrial side, we had this kind of multi-PDUs. So for example, looking at CANopen. In CANopen, we have the object dictionary with the objects that represent the data, the parameters, the functions on the device. And these objects, they were mapped into so-called process data objects, PDOs. And a PDO is then transmitted by a CAN message. And this mapping could either be static or dynamic, so during runtime by configuration, and also then depending on the size of the CAN message. So if we run CAN or CANFD, then a certain amount of objects could be mapped into the PDO and handed over to the CAN message. And also J1939 uses the same mechanism, just different terminology. So we have the data, they are called SP, suspect parameters. They are mapped into parameter groups, and the parameter group is then mapped into the CAN message. And actually, also for classic CAN, there was a possibility that the parameter group could have more than 8 data bytes, and so there was a transport protocol already specified for fragmentation of longer parameter groups. Now, as we learned already this week from Peter Fellnet, that there was a boost of J1939 or a new Vitamin, as he said, with CANFD, there's a new specification version, J1939-22, which now also defines a multi-parameter group protocol, which means also here we can now map dynamic several parameter groups in one CAN-FD message. Now let's look at Connexl. So in Connexl, we have the LLC frame with the identifier, then the protocol bytes. Then we have here at the end the LLC data. Oh, this is also wrong, from 1 to 2048 byte. And we have the data length code. And what is different compared to CAN, classic CAN and CAN-FD is that now a part of the Connexl LLC frame, we have one byte which is called the service data unit type. And the service data unit type defines the content of the LLC data, but also how the virtual CAN ID and the access address field is used, depending on the protocol. And so more or less, the service data unit type already is a reference which kind of application on top has handed over data to the LLC frame. And also then on the receiver side, then this information is used to pass on the data to the respective application. And there are several service data unit types definitions already defined, or at least intended to be defined. So we have tunneling of the classical CAN and CAN-FD frames. We have tunneling of Ethernet frames, of TCP/IP protocol segments, then diagnostic protocol segments. For sure, we will see can open FD messages. We will see J1939 messages, or also manufacturer-specific protocols. So the definition is more or less finished for first version of the protocol that is going to be released of the specification 611-1, which is going to be released soon. And then over time, as it becomes necessary, then more service data unit types will be added there. But since this is one CAN message, one Connexl message, and so we have one service data unit per Connexl message, this means only one PDU from the higher layer can be transmitted. We have a maximum length of 2048 bytes, but typically data is much shorter. So we really don't use the available bandwidth of the Connexl messages. And if we transmit then to PDUs only in the single CAN messages, as I just said, there's no efficient use of Connexl capacity. And also, since we have in the beginning the arbitration phase where we have the slow baud rate, then we have here with this protocol overhead also much more. We need much more time for the transmission. So the solution here is, of course, packing more than one PDU in one Connexl message. Before I go look deeper into this, I would like just to show you some use cases where this could make sense. So one use case is, for example, aggregation of various PDUs or signals transmitted by one ECU. So we have here a network. I just draw it with one gateway. There could be several gateways in between. But we have here ECU A1, and the ECU A1 transmits or has to transmit 3 messages. In that case, I just used AUTOSAR IPDU messages that this ECU wants to transmit. And we have different receivers of for the 3 data or signals that are transmitted. So now one possibility could be to transmit each signal or IPDU message in one Connexl message, or to pack all these 3 in one as a Multi-Pdo in one Multi-Pdo message, transmit this message. And on the receiver side, the receiving ECUs just take the data they are interested in. And we can also think about that signals can either be from one application or protocol type. So this could mean we have only homogeneous multi-PDUs, or that we have here different kind of applications, so different protocol types, and then we have heterogeneous multi-PDUs. A second use case is also from the AUTOSAR world. And this is, we have here, for example, also two ECUs transmitting different iPDUs. And here we have two ECUs receiving these iPDUs. And now what, in case we want to move the transmission of this signal from ECU A3 to ECU A2, then using multi-PDUs, it becomes quite easy, because we only need to tell ECU A3, you don't need to transmit the data anymore, and ECU A2, you need to transmit the data, but the receiver side doesn't care which ECU is the transmitter of this data, or with which Connexl message this data is transmitted. The same actually is possible on the receiving side. So if we want to move this signal, the process CPU, then we can just do the local modifications, perhaps even by configurations on the ECU, but we don't need to modify the network configuration. So the other ECUs are not affected by this. Of course, there's a drawback in such a scenario. Then we always have then a broadcast communication using the multi-PDUs. Then a different scenario could be the transmission of different higher layer protocols over the Connexl backbone. Let's assume, for example, we have a fire truck or an agricultural machine, construction machine, where typically all the engine part and perhaps the chassis part, they are running J1939. And then we have all that is on top of that. For example, on the fire truck, we have the pumps, we have perhaps the ladder, we have lighting equipment and so on. And this is typically controlled by CANopen. So we have different network segments on such an application. And we now could be able to have a kind of a backbone in this vehicle, which connects then the different network segments running CANopen or running J1939 then to the backbone. And on the backbone between the gateways, then the data is exchanged just by using multi-PDOs. So this means we could really have a very high bandwidth between these gateways. And of course, the same could apply just with pure CAN messages, as you've seen for Connexl in the service state unit type. We also have the possibilities to transmit classic CAN messages within the LLC data part or CANFD messages. And so we can also map several CAN or CANFD messages into one multi-PDU to exchange these messages on between gateways on the backbone. And the fifth use case is if we would have a gateway between Ethernet and Connexl. And this is also, again, of a use case more related to AUTOSAR. We could think of, so we have here ECUs running or communicating via Ethernet. We have here ECUs communicating via Connexl, and we have data that is exchanged, AUTOSAR data, by means of iPDU. And so typically on the Ethernet side, we have also these PDU containers, and so we just need then to take these PDU containers, get it out from the. Okay, now let's have a look at a possible solution for a heterogeneous Connexl multi-PDU. So we have here the LSC data, and this means we have here up to 2048 bytes. And we map then the C PDU. C represents or means contained PDU. So in each contained PDU consists of a header and a data, more or less as we have seen for the PDU container and AUTOSAR. And the data is then the contained data, and the header consists of a tape type, which defines the type of the PDU transmitted. Then we need a kind of a content ID, which is PDU or protocol specific, more or less, this gives the reference what kind of data is transmitted, and we need to have a data length. So we can then have this structure, and we can put then align several instances of this structure into one LLC data frame. So this is the basic principle. So nothing different, nothing complex. And just a few examples how this could look like. So if we now take the AUTOSAR iPDU, we have the data, of course, here. Then we have the PDU header, which is the PDU ID and the data length code. This we put into these fields. We have here then a Connexl specific C type or value that defines that the content is an AUTOSAR iPDU. And actually, this part here is more or less has already the same structure as it is in the AUTOSAR PDU container. So it could be easily forwarded between Ethernet and Connexl. Then looking at CANopen, in CANopen we have different object types. So we have network management, we have the sync emergency objects, we have transmit PDO, receive PDO, we have the USDO and heartbeat and so on. And one proposal could be that in the content ID, we have a data structure where we have the node ID from the node transmitting the data. Then we have an object type reference number. So which type of object? And then we have an object number. So for example, in CANopen, each device could have up to 64 transmit and receive PDOs. So if it's transmit PDO 2 that is transmitted, then we have here the value 2 for the object type, and then you have the object number 2 that is transmitted. And here for the content type, then we have the value that says us it's a CANopen PDU. The same for J1939. Just I would say the classic definition. We have the 29-bit CAN ID, and we just could take the complete 29-bit CAN ID and put it into the content ID field. We have the data length, which is only 3-bit here. Then we put it into this field, and we have the data with up to 64-bit or 8 data bytes. And here we have the value that says us it's a J1939 PDU. In addition to the protocol definition, we also need to think about how to, or when data needs to be transmitted, especially if we have a heterogeneous PDU on a device where we have, for example, this CANopen application, and we have a J1939 application running on this ECU. And usually they run these applications run more or less independent of each other. And each of these applications then passes on data which has to be transmitted to the Multi-Pdu module on the software implementation. Then the question is, when shall the software implementation or the Multi-Pdu module start with the transmission of the Multi-Pdu? Because it doesn't make sense that each time when new data is handed over that the Multi-Pdu is always transmitted, because then it's always one contained PDU in it, and we don't use the capabilities, or we don't follow the idea of the Multi-Pdu. And so the idea here is that there might be 4 transmission modes. One transmission mode, and these transmission modes could be, for example, configurable for various Multi-Pdos on one node, on one ECU. One node could be, for example, periodically. So the Multi-Pdo is transmitted periodically with the latest data, for example. Then there could be a timeout, and the timeout could be when a defined transmission timeout occurs. Typically, this could be, for example, in combination with these 2 transmission modes. One could be size threshold. So when the Multi-Pdu transmits a total size of all PDOs in the Multi-Pdu, perhaps this threshold could be configured. Then it shall be transmitted. Or perhaps that also the application can just trigger immediate transmission of the Multi-Pdu independent on how many data is in the Multi-Pdu, this could be, for example, be used for high priority messages. And then there could also be two communication patterns specified. One could be queued communication, and queued communication means that no data shall be overwritten by newer data. So it's important that the sequence of data is maintained. Or the other communication pattern could be last is best, which means that only when the latest data is important, for example, sensor data. So if the Multi-Pdu is on receiver side, if the data is not processed and newer data is received, then the old received data is already overwritten. And here I try to lay out the architecture on a Connexl device with a Multi-Pdo. So coming from the button, we have the physical layer, we have then the Connexl MAC, we have the Connexl LSC part, and then typically we have on top the application running. And now we introduce the Multi-Pdu, which is in between the application and Connexl LSC. So possibly the application can also decide if it wants to transmit the data directly or hand over the data directly to Connexl LSC layer or using the Multi-Pdu functionality. And as you also heard, we have security CAN-SEC in the future. So this means we also could secure these Multi-Pdus. And then there's also fragmentation. This was also briefly mentioned in these sessions, that if we have longer amount of data, longer than 2048 byte, then there could already be a fragmentation. How much sense it makes to have longer Multi-Pdus, I think this is something that is still needs to be discussed. And finally, just information for all of you on the status of the specification. So as you can see, the Multi-Pdu is also part of the CIA 611 series. 611 is a series dealing with higher layer protocols on Connexl. And part 1 defines, as I mentioned in the beginning, these SDU data types. And part 2 defines the Multi-Pdu mechanism. So the first draft is still in progress. So we will have a review of the first draft in July. But there are still some open topics that we need to discuss. Of course, one topic is, do we need heterogeneous or homogeneous Multi-Pdu protocol? We also need to select the protocols that we support in the first release. So more or less define these C types. We need to do a final definition of the Multi-Pdu transmission modes and communication patterns. So these are the major topics that we still have to discuss. But nevertheless, I expect that we will have a release of the first version of this specification expected in September, October this year. So yeah, this is the end of my presentation. I hope I could give you an idea on what we are working on the higher levels of Connexl.